Dr. Ted Venama Talks Audiology, the educational whiteboard series brought to you by Next Gen Hearing.
Hi, I'm Ted Venama, here to talk to you today about otoacoustic emissions. This can be construed as a counterpart to the test of acoustic reflexes that we spoke about last time. You'll recall last time when we talked about acoustic reflexes, we said that was a non-behavioral test, part of tympanometry, and it was used to test the function of the acoustic reflex, a non-behavioral type of phenomenon that occurs, the tightening of the little ossicles of the middle ear ossicles. Now, the acoustic reflex arc, we said, was an afferent thing. The inner hair cells speak to the brain. They send information to the brain. The outer hair cells take info from the low brain stem and serve in a more efferent, motoric type of function. Well, otoacoustic emissions is specifically a test of outer hair cell function, whereas the acoustic reflex can be thought of as a test of inner hair cell function. At any rate, the acoustic reflex and tympanometry arose or became popular in clinical practice in the 1970s. Otoacoustic emissions, on the other hand, occurred about 20 years later, or the clinical testing thereof became popular in the 90s. So the 90s is actually quite an exciting decade in the hearing health field, and here's why. That was the time when the different roles of the inner versus outer hair cells became popularized. Research had looked at it earlier, but it only emerged really into clinical practice, and its fingers were felt all the way through ripples of audiology, and it even had implications for hearing aid design, which is really quite exciting. At any rate, the inner hair cells afferent, the outer hair cells efferent. Now, figure 1 shows you this. You can look at that figure and you can see the inner hair cells within the scala media of the cochlea, and you'll see the outer hair cells in rows of 3 shown in that figure, also housed within the scala media. At any rate, when we take a look at basically what the ear is doing, sound hits the tympanic membrane, and then the middle ear changes or transduces the sound waves into mechanical piston-like motion, which wiggles the whole ossicular chain, and that vibration of the ossicular chain creates a tiny traveling wave inside the cochlea, inside the fluids and the basilar membrane, which is the floor upon which the hair cells all stand. At any rate, it's that hydraulic motion that excites hair cells. Which ones? Specifically, inner hair cells, and that hydraulic motion is changed or transduced by the inner hair cells into electrical impulses which are sent up the 8th nerve to the brain. Well, the cochlea is what we call tonotopic. In English, this means specific frequencies are represented in specific places in the cochlea. To be specific, at the wide base of the cochlea, treble or high frequencies are represented. At the narrow apex, it's the lows that are represented. This little diagram I drew here is showing you the role of the outer hair cells specifically. At any rate, if the traveling wave excites the hair cells at the base of the cochlea, you hear high pitch. If it excites the hair cells at the apex, you hear low pitches. So that's what we call the frequency representation inside the cochlea. It's tonotopic. But the fun begins when we look at how intensity is represented or neurally coded in the cochlea. You'll see this traveling wave I drew here. It has like a whoop, a little peak, and it's stimulating some low frequency portion of the cochlea. Well, it'll have its little peak, but the outer hair cells do 2 things here. First, they amplify the peak of that traveling wave. And secondly, they sharpen the peak of the traveling wave. Why does this happen? What's this for? Well, inner hair cells by themselves cannot sense soft sounds below conversational speech loudness. They can't pick it up. The fluid motion isn't enough to excite them. They need the mechanical action of the outer hair cells to help them sense soft sounds. Now, the outer hair cells do that. The cochlea is an amplifier. in that way. And like all amplifiers, you've got to pay the piper because all amplifiers distort. And guess what? The distortion created by the outer hair cells amplifying the peak of the traveling wave, that distortion is otoacoustic emissions. Sometimes they're called distortion product otoacoustic emissions. They are the byproduct of the outer hair cells working their tails off. You can think of it like you can have a light bulb which passes off a lot of light, but it also emits a bit of heat as a byproduct. Well, otoacoustic emissions are like that, a byproduct. Now, I said the traveling wave is also sharpened. Its peak is sharpened as well by the outer hair cells. And this has big implications as well. Because if you didn't have that sharpening, you'd have many different hair cells stimulated across a wide frequency range in the cochlea. The outer hair cell sharpening serves to increase the frequency resolution inside the cochlea, making it easier for the person to separate or distinguish among frequencies that are close together. If you don't have the outer hair cells, it's like you're combing your hair with about 4 teeth. When you've got outer hair cells, your comb has way more teeth and you have way better frequency resolution inside the cochlea. It's amazing what takes place inside that little snail-shaped cochlea. And hearing aids today, they can't sharpen the peak of a traveling wave, but they can amplify and focus their amplification on soft sounds, specifically to imitate the role of the outer hair cells. Because guess what? The outer hair cells, because they're the moving part in the cochlea, they tend to die first. And in any system, the moving part tends to go first. Just like in a CD player, it's the thing turning the CD that's going to go first. That's the mechanical part. Well, with outer hair cell damage, you have presbycusis, the inability to hear soft sounds below 50 dB. That's why presbycusis results in a mild to moderate sensory neural loss. It's damage to the outer hair cells of the cochlea, not really the inner hair cells so much, mostly the outers. So now let's cut to the chase as to how we measure otoacoustic emissions. All amplifiers, we said, distort, so you've got otoacoustic emissions. How do we measure them? Well, like tympanometry, we put a probe in the ear canal. It doesn't have to be airtight like in tympanometry because you're not changing air pressure inside the ear canal. The room just has to be generally quiet. Now, like tympanometry, figure 2 will show you, it's got 3 holes. 2 of the holes are tiny speakers, and they emit, each of them, a separate tone. The 3rd hole is actually a microphone that picks up the resultant distortion product otoacoustic emission. Here's how it works. The client is seated, the probe is put into the ear canal, and the 2 frequencies are put out. Now, it's very interesting. The 2 tones, research has discovered, the tones need to be separated from each other in terms of their frequency or pitch. They have to be separated by a 1 to 1.22 ratio. So for example, if one tone is 1,000 hertz, the second tone's got to be 1,220 hertz. These 2 tones are put into the ear out of the 2 little holes in the probe at about 60 to 70 dB SPL. They're put out into the ear, and a 3rd tone is picked up by the microphone. That's the otoacoustic emission. And in humans, the strongest otoacoustic emissions happens to be at 2F1 minus F2. Well, in English, again, that means 2 times 1,000 hertz, the frequency of the first tone, which is going to be 2,000, minus the frequency of the second tone. And it's at that particular frequency then that the otoacoustic emission will be if the 2 tones are 1,220 and 1,000 hertz. What we do in audiology is we emit pairs of tones surrounding 250 hertz, pairs of tones around 500 hertz, pairs at around 1,000, pairs at 2, pairs at 4. And in that way, we test the otoacoustic emissions resulting across the frequency range of human hearing. It's quite amazing. So figure 3 shows you then how the distortion product, otoacoustic emission, is actually lower than frequency 1 and frequency 2. You can see on this figure that you'll have a frequency of F1 and a frequency of F2, and then lower in frequency is the distortion product otoacoustic emission. And I stress the word lower so that people won't think, oh, that maybe that emission's just a harmonic of the two tones. It's not a harmonic. It's a intermodulation type of distortion, and it's unique to the cochlea, but not all that unique in the fact that the cochlea is an amplifier, and all amplifiers distort. And that distortion is done because of the amplification properties of the outer hair cells, not the inners. Otoacoustic emissions, you can think of them as like the ear in reverse. The sounds are actually coming back out of the cochlea, wiggling the ossicular chain, and then making the eardrum act like a speaker. It's the ear in reverse, and one might think, well, how come we can't hear them? Well, thank God we can't. Here's why. When sound comes into the eardrum is large, and then the footplate of the stapes and into the oval window of the cochlea is small. Pressure over a big area is converged onto pressure onto a small area, or a force over a big area is converged onto a force onto a small area, which increases pressure. And that's what the purpose of having a middle ear is in the first place. Well, when sounds go out of the middle ear, the reverse takes place. The otoacoustic emission becomes softer because sound over a small area becomes spread over a big area. So that's incidentally why we don't hear our otoacoustic emissions. However, another thing to be concerned or to realize is never confuse otoacoustic emissions with tinnitus. They're not. Otoacoustic emissions are an actual measurable sound that's picked up by the probe. Okay? Tinnitus is a symptom reported by a client, and only him or her, only that person hears it. And it's driving them bonkers, but it's not like a physician is just able to sit there and listen to someone's tinnitus, unless of course it's pulsatile, and then of course we know that it's more vascular in origin. But that's just something to take note of. Applications of otoacoustic emissions, fantastic. They are used mainly for infant hearing screening. An infant can't tell you what he or she hears. Otoacoustic emissions are tested along with tympanometry. Both of them are non-behavioral tests whereby to assess the hair cell integrity, otoacoustic emissions for outer hair cells, the acoustic reflex for inner hair cells. And here's why they are both good cross tests. Both of them are obliterated by middle ear pathology together. The middle ear is going to prevent the acoustic reflex, but it's also going to prevent the otoacoustic emission from exiting out through its space. Applications, again, infant hearing screening, and also they can be used as a way to test people who cannot or will not respond behaviorally to pure tones when they are presented. So they are wonderful as a screening test. They're not very good at testing the degree of hearing loss. Once you've got about a 30, 40 dB hearing loss, your OAEs are gone. Remember, they're only picking up soft sounds. So you don't have to have much of a hearing loss in order to have otoacoustic emissions gone. But they are wonderful as a screening test. I close with this that we had these are the very same two boxes, and I left them alone from the previous whiteboard on the acoustic reflexes. I want to underline this point. The word sensory neural in sensory neural hearing loss has two parts, the sensory and the neural. The sensory can be construed of as the outer hair cells of the cochlea. Good speech recognition, you'll still have that. You'll have a hearing loss, but you'll have pretty good speech recognition and present acoustic reflexes, albeit at reduced sensation levels, but still you'll have them. Inner hair cell damage isn't as common, but some unfortunate few do have it. And inner hair cell damage will result in poor speech recognition ability and absent acoustic reflexes. So you've got the otoacoustic emissions, whereby to assess the integrity of the outer hair cells, the neural afferent going portion of sensory neural loss is the inner hair cells. Once someone has a severe sensory neural hearing loss, more than a mild to moderate, it gets down into severe, then outer hair cells damage is accompanied by some inner hair cell damage. Outer hair cell damage results in up to about a 50, 60 decibel sensory neural loss. If someone presents with an 80 decibel sensory neural loss, chances are, or it's highly likely, that not only are outer hair cells damaged, but now also some inners are as well. And that goes a long way to explaining why people with severe sensory neural hearing loss have poorer speech recognition abilities. It all fits together like a big pizza pie. Anyway, thanks for listening. It's been a slice.